unpack that real fast. All right, so recording is rolling. It's Friday, October 1st. You guys just turned your forces quiz in, impact forums to do fifth period, and we're going to put the graphs together for this lab to figure out centripetal force. So what's the centripetal force to hold, say, this mass in a circle and along this radius of curvature at some particular speed? Right, there's some way, there's some equation that's going to combine those variables. All right, so switch my screen. Screen 2. You guys did 3 separate experiments to combine those 4 variables yesterday. Well, individually, you just did one or in teams. But we're going to put them all together and make one master equation by the end of class. All right, so the first graph I got lined up here. You guys ready to make some graphs? Who was in a team who wants to share your data? Who was in a team who was changing out the weight of the hanging canister? Who's changing out the weight of the hanging canister? Changing out the weight. I'll pass around class and see if I see a good paper that involves changing the weight. Weight is a. There's the looking for a variable weight. Oh, not that. Did nobody do one of these just by luck? Let's see. Aha, we're gonna borrow this one. All right, so I have an anonymous donor of data. And the weights on this page went, say, 970 millinewtons. Remember, we're doing grams and millinewtons yesterday. 1/1000th of what we usually do on paper. 800 millinewtons, 720 millinewtons, 610 millinewtons, 530. Whoa, what's going on here? Yeah, thanks, guys. Let's try it again. Okay, so 800. Okay. 720, 610, 530, 40, and 300 millinewtons. All right, now the corresponding speeds. Now, before I punch these in, let's rerun a quick hypothesis because you guys are about to get the answer. If you make that bottom Play-Doh canister heavier, do you think you'd have to spin the top one faster or slower? What do you guys think? Probably faster. Would that make sense? Faster? Okay. Well, let's see if the data confirms that. So the speeds went. Let's see. Just gonna copy these numbers, and we're gonna find out. Oops, I'm doing the wrong column. We're gonna go back. Just the plain V. What's up with a couple of these look like outliers, right? 1, 2, 3, 4, 5. What's this one right here? That's the largest. Does that correspond to? It's this one right here. Huh. Right. Just looking at these numbers, usually the speeds are somewhere in the ballpark of like 5 to 10 meters per second. So, I wonder what would the speed of this software factor of 10? Let me see. That does look a lot better. I'm gonna guess that's probably what it was. And then what about this one right here? I wonder if that was also off by a factor of 10. Let me just assume that it is and see what it looks like. Well, that would create like a perfect looking graph. So let's assume that's the case, and we're gonna run with this story. All right, so now, well, if you were in a group that was doing this, then yeah, thank you for sharing your data. You might have this graph already, but most of you guys can copy down this graph right now. This is on the front page. You guys see the top left graph that says V versus weight hanging at some constant swinging mass and some constant radial size. So V versus weight hanging. Okay. So your vertical axis is speed in meters per second. Your horizontal axis is the weight or force according to my Excel title, which weight is, of course, and that would be in millinewtons. So scale each of those axes about like it's scaled on the screen. Put those dots about where they go. And yeah, I asked you guys to hypothesize right before I plugged in that data. And yeah, you guys were right that the heavier you make that hanging canister, the faster you would have to swing it to maintain that circular path. All right, so next question though is, can we get more granular on what that relationship is between the speed and that hanging weight? Is that a direct relationship? Do you guys think that looks linear? Does that look linear? Probably not. There are a handful of graph shapes that you guys see throughout this class. I've shown you before. So there's like no relationship, just like a flat line, horizontal or vertical. There's linear relationship like y equals kx, which there's it could be inverse relationship, like one variable gets bigger, the other gets smaller. That's definitely not that. Do you guys remember a couple of graphs like power or root relationship? Power or root? That looks like it's probably what that is. In fact, that does look a lot like a square root relationship, doesn't it? Doesn't it look a lot like a square root? Which is exactly what it should look like. I forget if I mentioned this yesterday. I'm going to split my screen back over to projection. But this is one of those labs that if you're really meticulous about how you collect data, like making sure this radius stays constant and you're good with the stopwatch and whatnot, that it really shows up in the graphs. So this is a really good looking graph. Okay. So yeah, okay. I'm gonna remind you guys on what we're about to do is we're gonna manipulate some axes to see if we can pin down exactly what this is. I'm gonna go back to a just straight math, just y versus x. Of course, you guys have v versus f, but same idea, y versus two variables. And suppose you did have like a square root relationship. What if this was y equals the square root of x, just to keep it really fundamental? So, for example, if x is 1, y is 1. If x is 4, y is 2. If x is 9, y is 3, and so on. Okay. That like a great curve that looks like that kind of bends down. Okay. Now, since we've got some scientific data, we got to figure out, well, is it really a square root? What if it's a cube root or a fourth root or some kind of weird power? Like this is also, I told you guys before too, x to the 1/2. It's the same thing as a square root. Okay. What if it's x to the 0.6? Right. How would you know? So really what we're doing is we're making the guess that it's probably square root. We're going to manipulate the axes accordingly and see if the data actually follows. And if it does, well, here's what would happen if that's really true. So y equals the square root of x. Could you square both sides and make an equation that looks like this? Like y squared is equal to x? Like if I take this line and I square both sides, doesn't it look exactly like this right here? Y squared is equal to x. Okay. So this equation stays the same thing, but from different points of view. So this would be a y squared. The x-axis could still be x, but the y-axis, well, the vertical axis is no longer y. It's actually y squared. Is it? Okay. And that data would line up in a straight line. Okay. Now, it could be the same set of data. Maybe like point, 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 and this would be like point, 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 point. Okay. So it's the same data, but just on different sets of axes. Okay. Okay. Here's that. All right, so that's what we're going to do with v versus f, right? We're going to square both sides, get v squared as a function of force, which happens to be, if you look on your lab page, flip over to the back, see the very top graph says v squared versus weight hanging. That's what we're doing. Of course, it's some constant mass and swinging radius. Swinging mass and radius. All right, so flip back over to this. All right. So the data's already plugged in. And I had Excel ahead of time, was programmed. There you go. There's your top graph on the back. The one that says v squared versus weight hanging, v squared versus f. So you guys are drawing that graph right now? So v squared versus f. Now this is an abstract idea, like v squared. What is that really? It has units of meters squared per second squared, but it doesn't really mean anything by itself, like in isolation, but yeah, they do show a really nice direct relationship with that hanging weight. And what I can do, now the points are here, is right click on one of these points, go to add trend line, and oh, look at that. That is a direct relationship. So So by making the guess that it was exactly a square root, that does look pretty accurate. Okay. And one of the relationships is established. Now we know the relationship between the speed and the hanging weight. All right, so at this point, everybody should have at least two graphs. You should have the top left one on the front and also the top one on the back. Okay? You guys got at least those two, right? Right, next relationship. Let's go over to see what's the relationship between the speed and the swinging mass. Swing mass. So who was in the group who was leaving the bottom canister alone and leaving the radial size alone, but was changing out the mass of the swinging canister up top? Who was changing out the swinging mass? Oh yeah, Becca. What were? How many data points do you have?
We have 3.
Let's run with it. See what we get. So, what were your different mass values?
Different mass values. So we kept changing out like the mass swinging.
Yep.
26, 36, and 16 grams.
26, 36, and 16 grams. Okay. And okay, right before we come to the speeds, let's again do a quick hypothesis. As you make the swinging mass heavier and heavier, what do you think happens to the speed to maintain dynamic equilibrium? What do you guys think? Probably less and less, right? Like if the top one's heavier, you probably have to swing a little bit slower. Right? Let's see if that's true. So what were your speed values?
That would say the time 10 or the time 1.
Not time, speed. So the second to last column, it says just plain V.
Oh,
It says 2 pi r divided by
it
t.
was 2.98, 3.26, and 3.65.
All right. I guess what I'll do is, since there's only a handful of points, and sometimes it works, sometimes it doesn't, is I do have, well, let me see what last class got. Oh, yeah, I think last class, actually, this worked out pretty well. So let's copy theirs. So that's what their graph looks like. So let's run with that. So this is the bottom left graph on the front page, one that says V versus mass swinging at, of course, constant weight and radius. So the vertical axis is speed in meters per second. The horizontal axis is mass and grams, because you're doing grams. Okay. And I asked you guys to hypothesize right before you guys saw the numbers punch in. And you guys were saying, oh, well, it does make sense if you make the top canister that's swinging around heavier and heavier, you would have to swing it a bit slower as you were doing that to maintain a constant circle. And yeah, that's exactly what this data shows. It shows an inverse relationship. See, one variable gets small, the other gets big. One variable gets big, the other gets small. So inverse relationship. All right, so we're going to go through that axis manipulation process like I did for the that last pair of data. But if it's an inverse relationship, the axis manipulation is going to be, well, we have to take the reciprocal of one of those variables. And the way that this lab is being to put together all the data at the end, to put together all 3 different experiments, it's all going to have to relate to some variable, which is ultimately going to be the square root of the speed. We don't have to do it that way, but I think it's the easiest way to do this lab. So let's do the reciprocal of the mass. So the next graph, the one on the bottom right on the front, see the bottom right graph says V versus 1 over M. You guys see that one? V versus 1 over M. That's the one I'm about to show you. Now, this was the data's already plugged in. I just had Excel take the reciprocal of the mass values and replot. And now it looks like that. So this is the bottom right graph on the front. Bottom right graph on the front, V versus 1 over M. And so label the vertical axis V, the horizontal axis is the reciprocal of the mass. So V in meters per second, 1 over mass would be 1 over grams. And scale those axes about like they are up there. Put those points about where they go. Now, I do see from this point of view that as one variable increases, the other increases. Of course, one of those reciprocal, but sorry. Okay. Is that graph showing a direct relationship exactly? Or how many guys are looking at those data points thinking, that kind of looks like a square root relationship, kind of like the last one. Does that look kind of like a square root relationship again? Yeah, kind of. Sure. I mean, I can imagine that there's maybe a curve that goes through these points that kind of hooks down, kind of bends downish. It kind of looks like that, doesn't it? And if you thought that was the case, then you are right, at least by the textbook answer to this lab. So we're actually going to put this set of data from this experiment through another axis manipulation, and that's to square the speed again, just like we did for the last one. So again, if you suspect that this is a square root relationship, the way to test that out would be you could square your y-axis value, in this case v, replot the data, and see if that would show a direct relationship. Are you guys ready for the next graph? Okay. So that is, continuing off the same set of data, if you flip your paper over and look at the middle graph, see the one that says v squared versus 1 over mass? V squared versus 1 over mass? It's the one in the middle. All right, I'm going to scroll over to that line. So same set of data, just let Excel do its thing, and there you go. That's what that data looks like. Okay, so that's not maybe perfect, but that's pretty close. That's probably close enough to a direct relationship, which the textbook answer would say that should be a direct relationship. So there you go. Phew, we got a double manipulation going on. So the speed is squared, mass found the reciprocal values, and those points happen to line up in a direct relationship, like a straight line. All right, so at this point of this 3-part experiment, we've got all the relationships, we've figured out all the relationships except for one. The one we haven't incorporated, the one variable we haven't brought in so far is the radial size. So there's one more group to go. And while you guys are writing or drawing this graph on the back, so you guys got the back side of the lab, you guys see these 3 graphs on the back. Do you guys notice that these 3 graphs on the back are all v squared versus something? So the top one's v squared versus weight. You guys did that a few minutes ago. The one you guys are doing right now is v squared versus the reciprocal of the mass. And the one we're about to do in a couple minutes is v squared versus radius. It's all v squared versus something. So that's how these are all going to be tied together, is through v squared. You don't have to do it that way, because it just happens to be the easiest way to do this lab. All right, you guys ready for the last set of data? All right, so I'm going to switch back over to period 4. We're going to go, I'm curious to see your guys' versions of those real fast. So there's v versus 1 over m, v squared versus 1 over n. Okay. All right, who was in a group, who wants to share your data, who was changing out the radial size, but left the 2 canisters alone for the entire day? Who was changing out the radial size? Okay, yeah, Israel, what were your radial values? 0.09, 0.23, 0.9, 0.03, 0.15. All right, and let's go on this one. Yeah. All right. Also, right before you give me the speed, so let's again do a quick hypothesis. So, say as that radius was increasing, do you think you'd have to swing faster or slower? What do you guys think? So go ahead and tell me, what were your speeds? 1.53, 2.78, 379, 0.43, 157, 2.37, 4.5. All right. Hey, that looks pretty good. That's about what that should look like. Nice. So this is the last graph on the front. So right now you guys are drawing the one, the top right graph on the front. The one says V versus R. Right, so speed versus radius, and of course constant hanging weight and constant mass. So leaving those two Play-Doh canisters alone. V versus R, the top right graph on the front. So V is in meters per second, R is in meters. So these are all decimal values. Scale those axes about like you see there, put those points about where they go. And what is definitely standing out on that graph is that the larger the radial size, the faster it has to swing. You guys see that? Okay. Tell you what though, I'm going to give you a tidbit from future in this class. Okay, again, while you guys are copying this down, give you guys a little bit of extra information. So normally I like to teach this class in a little bit different order and teach you guys some other stuff before we get to this lab, but your textbook and also AP does the same thing. They push us ahead a little bit, so I'm trying that out anyway. So what I'm saying is that normally at this point in the class, you guys know a little bit of extra information, and that's that there's actually two different kinds of velocity. So the velocity that the only velocity we've been dealing within this class is called linear velocity, like meters per second, like how fast. But if you think about it, you guys ever heard something called revolutions per minute, like RPM? That could refer to a spin rate, couldn't it? Like how fast something is spinning. And for example, the Earth. The Earth has a certain spin rate. Sometimes I say the Earth is spinning at like 1,000 miles an hour, but that's really only true near the equator. If you get up near the pole, that's closer to zero. But no matter what your latitude is, everywhere on Earth has the same spin rate, and that's one revolution every 24 hours for the whole planet, right? And in this class, when we get to this point in class, the unit we usually use is radians per second. Okay, so I'm introducing this idea to you guys that there's actually two different kinds of speed, right? There's linear speed, which you guys have seen lots of times in class, and there's angular speed, which is how fast something's spinning, which is a future topic. And I'll tell you guys what too, is that even though linear speed is increasing with radius, that's exactly what that graph shows. If we went with the other kind of speed, the opposite would be true. There would actually be a slower angular speed. So that's a future topic. It's not worth it. Do you guys think that this could be a direct relationship? Does that look approximately direct? I think it does. But the textbook answer is that this is also ends up being another square type relationship. So the curve of best fit would be, again, one of those curves that like hooks down, like a square root type, right? Which means we're going to do the same axis manipulation that we did for the first one and also the second one of the second one. So we're going to do V squared versus R. And that is going to be the very last graph on the back side. Okay, so flip the paper over, go to the very bottom, graph, see what one says V squared versus R. Okay. Now this ideally would line up in a straight line. Actually, that's pretty close, isn't it? It's a line of best fit. There you go. Just like that. So go ahead and copy that one down. And so V squared versus R, that's a direct relationship. Interesting. So if you were to double the radius, you'd have to like quadruple the speed, right? Something like that. Triple the radius, be 9 times the speed. Or is that right? V squared, yeah. Squared. No, I'm sorry, I got that backwards. If you did quadruple the radius, that'd be twice the speed. If you did 9 times the radius, that'd be 3 times the speed. That's how it works. Right. So we've got all the relationships. Now, again, mentioned this before, notice that those 3 graphs on the back are all V squared versus something. But that links all the variables in this lab, all three parts, right? All three experiments. So now we're about to put this all together. You guys see these couple boxes down at the bottom? Now these are, the same idea, just from different points of view. The box on the left is going to directly link those three graphs together, and then the one on the right is just a rearrangement. It's going to be towards what we're actually trying to solve for. So the bottom left box says, how are those four variables related? Okay, force of the hanging one, mass of the swinging one, the speed of the swinging one, and the radial size of the circle. How are those related? And the three graphs above exactly link to the answer. So the top graph says that the square of the speed is directly proportional to the weight hanging. Now remember that weight hanging is providing the tension, which is providing the centripetal force that's holding everything in a circle. So the weight hanging, I'm actually going to call centripetal force, F sub c. Okay. So F sub c represents centripetal force. Okay. The second graph says that, whoops, it didn't mean v, I meant v squared. That's what I meant, c v squared. Okay. The second graph says that v squared is directly proportional to the reciprocal of the mass. So I can make a giant fraction over here and put mass. Okay. So as mass increases, the speed would decrease, I think. And the third one, the one you guys just made, says that speed squared is proportional to the radius of that circle. So it would go like that. Okay. That is the answer to the bottom left box. The square of the speed is proportional to centripetal force times radius divided by mass. Okay. But the whole point of this lab is to say, what's an equation for centripetal force? Say, what is the force to hold something in a circle? What is the force of turning steering wheel in a car to, say, on some curved path, right? Where of known radial value. Say, if you need to mass the car, right? The speed of the car. Right. So all you have to do is algebraically rearrange this and solve for centripetal force. So centripetal force, F sub c, again, represented by the hanging Play-Doh canister in millinewtons or newtons. Let's say you cross multiply up the m, and you get m v squared, and then you take this r and divide it down and do r. I meant to make a proportional sign. Okay. A proportional sign is kind of like an equal sign, but it's saying, well, maybe you're possibly leaving off part of the story, like maybe a 1/2 factor or maybe other variables or something like that. Okay. Technically, that's all we proved in this lab is proportionality, although it is true that this is exactly equal to. There's nothing else to this equation. So centripetal force actually ends up being mv squared over r. Now, last points of commentary, that's the bottom right box on the bottom left. So points of commentary here is that centripetal force is always supplied by one of the forces that you're already familiar with. So it might be a tension in a string, it might be a weight, it might be some component of a normal force, but it's never a force unto itself. It's some force that's always acting as a centripetal force. Okay? And then also I want to give you guys another example of this. So you have one example of everything you did yesterday, but here's another example. Say you're in a car and you're going around a curve. Now, how could you be going around a curve? Either there's friction between the tires of the road, or the road is banked, so there's some component of a normal force, but there's some force that's causing the car to turn. How big is that force? Well, it'd be the mass of the car multiplied by the speed of the car squared. So you look at your speedometer, it says you're going 30 miles an hour. Okay? Divided by the radius of curvature of the road that you're on. And then you can figure out exactly what the force would be from road to push that car in a circle. That's it. All right, so turn that lab into the gray trick, and we are done for the week.